In this short recording, we're going to have a very quick look at MATLAB and programming, I guess, from a generic point of view. I want to touch on what programming is and where it fits into the engineering process. I'm going to very quickly go through some basic MATLAB constructs, and I'll touch on this idea of structured programming, but that's going to come out a lot more as we go through examples in the workshops during semester. A key thing, however, that you all need to remember is that you did learn MATLAB in Eng 1060. Okay, I am going to assume you know how to program in MATLAB. I am not intending to teach you in this unit. If your MATLAB's pretty rusty, then you're going to need to brush up on it. So, let's have a look at a general engineering analysis. And that's shown here sort of schematically in this graph. If we have a real-world problem, the first thing we need to do is we need to go out there, we actually need to define what the problem is. And this might seem really obvious, but in actual fact it is often the hardest thing to do in a genuine engineering situation. You know that something's not working, but what's causing it? Once you actually understand what it is you have to solve, you may then need to go away and measure some data. You might choose some particularly relevant theory, and using all of these things, often you will develop a mathematical model. So in other words, some mathematics that describes what the problem is and then maybe gives you some clues on how to solve it. Once we have our mathematical model, we then need to use problem-solving tools to solve the model. These include computers, statistics, numerical methods, graphics, a whole bunch of other things like that. And so programming, what we're doing in this unit, fits very firmly in this area here of problem-solving tools. And to some extent also producing numerical and graphical results that we can then use to do something with. Hopefully implement a solution. But this bit down here is not part of this unit. For a few cases, the exact solution of our mathematical models that we develop here will be available, but that is not true in general. So in most cases, you will need some kind of computer model to solve the problem numerically, and that always means approximately. What is a computer program? Well, it's merely a set of instructions that direct the computer to perform certain tasks. Okay? A computer never does anything other than what you tell it, unless it's about to break down. Programming style is really essential in engineering numerical modeling. And when I say programming style, I mean good programming style. It's also important in this unit. So what do I mean by programming style? Well, it's a little bit hard to describe exactly, but if you have good programming style, it allows people, and this includes you, to read and easily understand what your code is trying to do. So why is good programming style important? Good style will make it much easier to get your code working, in other words, to debug the code. It'll make it easier to use the code as it was intended. Importantly, it's going to make it easier to extend and reuse the code. And of course, for most of the students here, it's going to help you get good marks in this unit. So, good programming style is important. So, let's just quickly go through a couple of MATLAB things. I want you to use comments when you're coding in MATLAB. Remember, the comment line starts with the % symbol in MATLAB. Any M file that you submit in a computer lab should have your name, date, your ID, and the assessment task that this is trying to solve. You should give a brief description of what the M file is supposed to do and a description of the key variables. And please use meaningful variable names throughout, because this will help you debug your code. Comment the code throughout the M file so that you're telling yourself, when you come back to look at this a little bit later, what you're trying to do. And structure the code so it's simple and readable. So structured programs are always easier to develop, debug and test, and take a much shorter time to update. And in this unit, what I'm hoping to do is get you to use previous bits of your code in future laboratories. So if you've done this well, it'll be much easier for you to use them in the future. You'll hear me use the word algorithm quite a bit in this unit. So what do I mean by an algorithm? Basically, it's a set of rules that precisely defines the sequence of operations needed to solve a problem. And any numerical algorithm can be composed of three fundamental control structures. You will have learned these in Eng 1060, but I am going to quickly go through them again. Sequences, selections, and repetitions. And we need to quickly look at each three of these. So a sequence is a linear set of steps that never changes. In other words, every time you run this bit of code, you're going to do exactly the same things in exactly the same order. So something that looks like that, schematically in a flowchart diagram. And if, for example, have a little bit of code here written by my colleague Je, we see that there's 1, 2, 3, 4, 5 lines of code. Every time this bit of code is run, these are executed in exactly the same way. A selection provides the means to split the program's flow into branches based on the outcome of a logical condition. What does that mean? It means an if test, effectively. And there are two fundamental ways of doing this. They're almost the same, but not quite. The first one is we come to a particular part in our code and we test whether some condition is true or false. If it's true, we go down and we execute some things that we put into this block of code here. If the condition is false, we don't do anything. So that's just an if test. The alternative is an if-else test. We come down to a particular point in our code. Again, we test for a condition. If that condition is true, we go down and execute the things that are in this block of code here. If the condition is false, we go down the other way and we execute things that are in the false block. You should all be pretty familiar with these. So an example, find the roots of the quadratic equation ax squared plus bx plus c. We know that this is the roots, but what happens when b squared minus 4ac is less than 0? We don't have any real roots. Let's imagine we're only interested in the real roots. A bit of code, or a bit of an algorithm I should say, to use this would be the following selection. Our test is b squared minus 4ac bigger than 0? If it is, then we use this formula to calculate the roots. If it's false, we print a statement. Output has no roots, or perhaps no real roots. And here's a bit of code that does that. So here's the if, the else, and the end. So if this is greater than 0, then this is our true block. Else, that is our false block. Repetition is the other coding structure that we need, and it basically means implementing the same instructions repeatedly. In other words, these are known as loops. And again, in MATLAB there are two types, and they are distinguished by how they are terminated. So the while loop basically comes down and says, okay, let's check this condition. If this condition is false, we're going to exit. If the condition is true, we're going to go down here. We're going to execute some commands, a block of commands, then we're going to go back up, and we're going to test the condition again. If it's false, we exit. If it's true, we go around and we keep on doing this. So a while loop is the construct you use when you don't know how many times you need to execute this set of instructions down here in block 2. So for example, when you're trying to converge and get an error less than 10 to the minus 6, the condition might be while error is bigger than 10 to the minus 6, execute our code. As soon as it's less than 10 to the minus 6, in other words it's false, we exit. The other kind of loop is a for loop, and a for loop is used when you know exactly how many times you need to execute a set of instructions. So you might have 1,000 data points and you want to do the same thing to those 1,000 points. You want to divide them by 100 or something. You'd use a for loop, and so a for loop requires you to have a counter, which we're going to call I. It's going to have a start value, it's going to have an increment, and it's going to have a finish value. And so basically a for loop goes through and checks to see if this counter is bigger than the finish value. If it is, we exit. If the counter's not bigger than the finish value, we execute our code. So that's a for loop, and you'll need to use those. So all of these things form nice parts of structured programming. There are other things in there like M files and functions that you will also need to use. We will look at some of those things in the workshops. Where it comes to structured programming, the thing that I probably do need to mention is that there is no single correct way to do practically any bit of computer programming. There are multiple correct ways. My recommendation is when you're coding is to use what seems simplest and what seems the easiest to you to understand. The thing that is most important when you're doing structured programming is that your clarity of purpose is there to see. That you can look at the code and you can understand what it's doing. So that means using comments. That means structuring your code to look as far as possible like the mathematics, and doing things in a logical and sensible sequence. Okay, key points from this recording. You need to be familiar with MATLAB. It's going to be important for you to get good marks. Next recordings, we're going to be looking at vectors and matrices and the solutions of linear systems. So these are also going to be important aspects of this unit.